A very simple way for detecting deadlocks is a timeout mechanism. If a transaction is waiting too long for a lock, the timeout mechanism assumes it is in a deadlock situation and aborts it. Another way is building a graph called wait for graph. The nodes of this graph are active transactions. The edges of this graph correspond to waits for locks. So, if transaction Ti is waiting for transaction Tj to release a lock, there will be an edge from Ti to Tj. The edges are added when requests arrive and queued while waiting. They are removed when lock requests are granted, and therefore the wait is resolved. For example, in figure A, T1, T3, and T4 are all waiting for T2 for locks they need. If the system is in a deadlock state, the wait for graph will have a cycle. For example, in figure B, T1 is waiting for T2. T2 is waiting for T4. And T4 in turn is waiting for T1. So there is a deadlock situation involving these three transactions. Now that we detected the deadlocks using wait for graphs, how do we resolve them? Resolving a deadlock can happen by aborting a transaction within the cycle causing the deadlock. For example, aborting any of the T1, T2, or T4 in the wait for graph here can break the cycle in the graph and resolve the deadlock. However, we need a criteria for choosing that transaction to abort. That criteria is usually picked in a way for the abort to have the minimum possible impact on the performance of our database management system. Our criteria might be choosing the transaction with the fewest locks, or choosing the one with the least work done, or the one farthest from completion. Note that in the first choice, we are trying to reduce the possibility of getting into the same situation with the locks again. While in the least work done and farthest from completion, we are trying to minimize the lost work. To prevent possible starvation, we try to avoid aborting oldest transactions, and also favor the transactions that have been aborted and restarted again. The aborted transactions can totally roll back, or if possible, roll back to the point that they can release the lock that has caused the deadlock. We said, in practice, deadlocks are infrequent. They are also proven to be fairly preventable. But how? Prevention schemes can be effective when there is high probability of deadlocks. One prevention scheme is achieved by assigning priorities to transactions. Priorities can help break the cycle of wait for graphs. The priority scheme can be based on timestamp of a transaction's start time. This is because it is a good indicator of effective aborting of the transaction on the performance. Different policies can be used. For example, when transaction Ti requests a lock and Tj has the lock that Ti is requesting for, the wait die policy says if Ti has higher priority, it is allowed to wait. Otherwise, it should be aborted. And another policy, wound wait, could also be used, in which Tj is aborted for the requesting Ti if Ti has higher priority. Another possible solution for the deadlock prevention is conservative two-phase locking. In conservative two-phase locking, which is a variant of two-phase locking, transactions acquire all locks that they will ever need from the beginning till completion. This removes the possibility of deadlocks and reduces the average time of wait. However, since locks are set at the beginning, it might end up setting more locks than actually necessary.